This is going to be our last lecture on covering spaces. We can obviously say a lot more about covering spaces, but then we're going to be going overboard. So we're just going to just talk about this last remaining topic, and then we'll move on to new ideas in algebraic topology. To begin, let's ask this question, and we did ask it before, but let's say that X is the figure 8 space. So you would just take two circles and you would connect them at a point. So that's the figure 8. And then you pick a point, let's say P, that's the point at which the two circles join. And then we can ask, what is the fundamental group of the figure 8 at that point? It really does not matter what point you pick. They will all be isomorphic groups. But let's just, for concreteness, pick the point where the two circles come together. So what would be the fundamental group for that? And the way you would do this is you would draw two loops. The orientation does not really matter. So let's say you call this one A. That's the loop that goes around that way. And then you have another one. Again, the orientation does not really matter here. Let's say this is going to be B. So you have two loops. And intuitively, it makes sense that this loop and that loop, they're not homotopic to each other because you have all that empty space. You cannot move A into B. And what this is that this is what we say, this is what we call a free group generated by A and B. We are being a little bit sloppy over here. When we write A, we really mean the homotopy class of A, of course. So what do we mean by a free group? So it just means that it's free from any relationships. There is no relationship that exists between A and B. Intuitively, that makes sense because there's nothing you can do with A to move it over to the other side. But when you actually write it out in algebraic notation, what this would mean is you would have the identity. So that would just be the constant path P. So that's the identity. That's the constant path that stays at P. You always have that in the group. Then you will have A, you will have B, and then you will have A squared. A squared would just mean you go around twice. You will have B squared. You can have AB. AB represents the path, the closed path where you go around A first and then you go around B. You can have AB inverse. This one will represent going around A with that orientation, and then B inverse means you reverse the orientation. That would just mean going around like that. But then you also have BA. BA, that would mean you go around like this and then like this and so on. BA, you can have B squared, you can have B cubed, then you can have A inverse, B inverse, and so on. You can also have ABA. ABA would mean you go around A, then you go around B, then you go around A. B inverse, you can have AB squared A, and so on. When we're saying that it's free, free just means that all of these are different. And when we say that they're different, we mean they're non-homotopic to each other. That's what it means. So what you're basically saying, so basically the fundamental group are all words, so words in quotation marks, so these are not English words, these are just symbolic words, that can be formed using the letters. I put letters in quotation marks because we're just symbolically, that is what we're doing. But of course, these letters represent homotopy classes of loops by using the letters A and B and their inverses. You can also throw in the inverses, but that's what it is. So it's all different words you can form. And that's the reason why. So you have words and you have letters, and all of these words are different. And that's why we call it a free group, because there's no, there is no relationship that will allow you to turn one of these words into a different word. Now, an example of something that is not free would be when we talked about the fundamental group of the torus. So when we have the torus, we saw that if you pick some kind of base point P, we saw that you have a loop going around like that. The orientation does not really matter, how you choose to orient it. And then you have a loop going around like this. We call this A and B. so one of them is A and one of them is B, there's a relationship that AB is equal to BA. So when you start writing down the words, if you have, let's say, ABABBA, that would be the same thing as you can just put the A's in front, and then you can put the B's after that. Because you have this commutative relationship, it allows you to interchange them. And in the end, you end up getting A cubed, B cubed. So that's the reason why the fundamental group of the torus is isomorphic to 2 copies of Z, because you can always put the A symbols in front, you can put the B symbols at the end, and then you indicate how many times, how many copies of this symbol you use, and then how many copies of that symbol you use. And in the end, you just get a group that is isomorphic to a product of 2 integers. This group is not isomorphic to a product of 2 integers. This group is not abelian, that AB and BA are different. So that's what we mean by a free group. So you have 2 generators. So in general, we talk about what we call a free group of rank, let's say R. So the rank just means how many generators. So the fundamental group of the figure 8, this is isomorphic to, again, it does not really matter what base point you use, but this is isomorphic to a free group of rank 2. There's 2 generators. Now, the fundamental group of the circle, that is isomorphic to the integers, but the integers is actually a free group of rank 1, because like if A denotes the loop that goes around 1 time, then you have A squared, that means traveling around twice, and so on. And then you have A inverse, A to the negative 2, you have the identity. So in general, a free group is not abelian, but if the rank is equal to 1, then it's isomorphic to the integer, so it is abelian in the special case when the rank is 1. I guess we can make a free group of rank 0, This is a bit degenerate. It's like one of those like empty set conventions, but maybe we'll adopt the convention that this is the trivial group. Though one might complain and say that the trivial group is not a free group, because if A represents the identity element, then you have the following relationship, that the identity is equal to itself squared. So then you're contradicting the fact that you have no relationships. But let's not make a big deal about this. Let's treat this maybe as a degenerate case. Now, let's ask this question: how do we justify that the fundamental group of the figure 8 is isomorphic to a free group of rank 2? You had this question on the homework, but I want to go over the explanation again because it's very nice. So it has to do with the universal cover. So let's say X is the figure 8, and Y is the universal cover of X. So the universal cover, it is a covering space that is simply connected. And the way you get the covering space, we did talk about this before, it's a very nice picture. It's that infinite tree. So let's say we call this one the A loop, and we call this one the B loop. And you can choose an orientation. It does not really matter so much here how you choose to do it. The way you get the universal cover is this infinite fractal tree. So you basically have something going like this, then you cut it down the middle, you cut it down the middle, you cut it down the middle, kind of keep on making it smaller, and then you make it go like this. You make it go like this, and then you kind of make it, and then you make it smaller like this. And then each one, kind of make them smaller. I'm not going to draw the whole thing, but just enough to give you an idea. And then this one is going to be A, so this is the one that gets mapped to A. So the covering maps this path to a closed loop. And then the ones that go vertically, this is the one that gets mapped to B. Then this one gets mapped to A. This one gets mapped to B. This one will get mapped to A. This one also gets mapped to A. So the ones that go vertically, they're the ones that go to B. Now, if you go in the opposite direction, then that will just go in the opposite orientation. So this is the one that's going to go to A inverse. So if you imagine you have a path from the origin to wherever that is, you're just going to travel in the other direction. And this is going to be, so going down, that's going to be B inverse like this, and so on. This is going to be B. So you have a covering, you have this covering map pi from this fractal, from the fractal tree into your space. And now here's the crucial observation. So observe two things. So first observe, so there's two things you want to observe. The fiber over the base point. So the base point is going to be where the two circles meet, are the branches on the tree. So what I mean by the branches on the tree, so what I mean is this is the point where the two circles meet. And now if you look at the fiber, if you look at all of the places on the tree that get mapped to that, there will be all of the places where these lines they meet. So we're going to call those the branches. And of course, there's one going like this, of course. I'm not drawing the whole thing, so these will be your branches. So the fiber over the base point will be the branches. Okay, the second thing you want to notice is every loop in X, so X is the figure 8 space, will lift. So loops will lift to a path, which starts at the origin, 0, 0, in Y, so that's in the tree, and ends at one of the branches. So we've talked about this before, that when you have a covering space, if you take a loop and you lift the loop, it will in general lift to a path. And the terminal point of the path will be one of the points in the fiber. So therefore, let's say we make the convention that the origin gets mapped to the origin. This point gets mapped to the origin. That's the way we choose to do the initial condition. And once you've made that choice, when you lift your loop, its terminal point will stop at one of these branches. And then the third thing you want to notice is at each branch, there is a unique path along the horizontal vertical segments from 0, 0, that's the initial condition, to that branch. Okay, so what we're saying is, let's say you have a closed loop and you lift this loop, and when you lift the loop, you're going to look at the terminal point, right? So where does it end? So let's just say it ends right over here. Let's say it starts here and it ends there. So there's a unique path. So it goes A first, then B. There's a unique way, there's a unique path to do that. Because it's a tree, right? There's only a unique way you can travel along those segments. And so what follows from here is the sequence. So thus, there is a unique sequence of A's and B's along with, inverses, because sometimes you go in the opposite direction. It's possible, for instance, that the branch is not over here, but maybe down there, and then you have to kind of travel in some negative directions as well. But there's a unique sequence of A's and B's from 0, 0 to that branch. And so and it follows from here. So it follows that every loop in X is homotopic to a unique sequence of A's and B's along with their inverses. And that explains why the fundamental group of X is a free group generated by these two loops. That's what it has to do with. So that's the explanation, and it has to do with the universal cover. Now, this actually generalizes in a nice way. We can generalize. So we can generalize this result to what is known as a bouquet of K circles. So a bouquet of K circles just means you have a circle then you have another circle, you have another circle. So you have like lots of circles all meeting at a single point. So in this case, we have 1, 2, 3, 4, 5, 6 circles. So let's say this is X. So then the fundamental group of X at the point where the circles meet, this would be isomorphic to a free group of rank K. K is the number of circles, and the generators would be every loop. So if this is like your A, and then this would be your B, and so on. So it would just mean that every loop in X would be a unique product of all of these individual loops for every circle that goes around it. And it's the exact same argument. Like if you had, let's say, 3 circles as opposed to 2 circles, then the universal covering would be a fractal tree, but not in the plane, but in the 3-dimensional space. But it's the same idea. And then this argument will generalize to as many circles as you want. So this is what we call the fundamental group of a bouquet of circles, and we'll be using this later on in the lecture. So it makes sense to sort of mention it right now so that we can refer to it again when we need to. Now we're going to talk about what a graph is. We need to give a warning first, is that there's a difference between what we call a discrete graph that you see in, let's say, some kind of discrete math course versus a topological graph. They're very similar concepts, so it makes sense why we call both of them graphs, but they're defined a little bit differently. This is probably what you've seen before. You've probably seen what a discrete graph is. So a discrete graph is, so it is a pair, V comma E, where V is a set of vertices, and E is, let's say, you could say a set of sets, but I'll just say a collection of 2-element subsets of V. So for example, let's say V is 1, 2, 3, 4, 5. That's the set of vertices, and the set of edges will consist. So it's a collection of 2-element subsets. So here's a 2-element subset. Here's another 2-element subset. Let's have one more, 1 comma 5. And the way you represent this as a picture is you draw your vertices. So those are your the vertex set, and then you use the edges to draw an edge between them. So between 1 and 3, you're going to have an edge. Between 2 and 4, you're going to have an edge. Does not matter how you draw it. And between 1 and 5, you're going to have an edge. So this is what you call a discrete graph. Now, when you're dealing with a discrete graph, the fact that it goes around like this does not matter. You could, of course, connect them by a line directly from 2 to 4. The place where they intersect, that's not part of the graph. These lines, they're not part of the graph. Those lines only show the relationships that exist between the vertices. So you do not really care so much about how you draw it. So this is what we call a discrete graph. This is not a topological space. Where they intersect does not matter. How they intersect would not matter. You only care about the vertices and the relationships that show, the edges show the relationships between the vertices. So that is what we call a discrete graph. This is probably the way you've seen a graph defined before. But we're going to be doing topology, and we're going to define a graph a little bit differently. It would be kind of similar to this, but it's going to be defined differently. In a topological space, we will actually care about the points along the edges as well. The edges are not just drawn visually to show the relationships, they're actually part of your space. And then it will actually matter if you cross over, because if, like, so imagine this, if this crosses over, then that means your topological space is connected. But if, let's say, the edge actually goes behind the other one, then that would mean your graph is disconnected. So you are changing the topology, and therefore a topological graph would be a little bit different. Now, one thing you want to keep in mind before we write down the definition is in a discrete graph, we specify a vertex set and an edge set. In a topological graph, we start with a topological space first. There's not going to be a set of vertices, and there's not going to be a set of edges. You're going to start with a topological space first. So let's write down the definition. And I should just give you a little bit of a warning that depending on what source you use, they might define this a little bit differently. Now, all of these definitions in the end, they're going to be equivalent to each other. But the reason why I want to define it this particular way is because later on in our course, you're going to see this very same definition generalize to higher dimensions. So it makes sense to first define it for one dimension, so then you're going to be more comfortable when we do it for higher dimensions. So it's just like, I think, a very nice generalization that you will see follow later on. So this is going to be the definition that we will use. Definition. So let X be a, so maybe I should just call it G, in fact. Let G be a topological space. We say G is a graph, so a topological graph, if and only if G has what is known as a one-dimensional triangulation, which we're going to define what that means. It has a one-dimensional triangulation. So in other words, i.e., there is a collection of mappings. So I'm going to call these mappings F subscript lambda instead of F subscript I, because I do not want to confuse the indexing set with the interval, with the unit interval. So I'll write it like this: F lambda, where lambda belongs to some indexing set capital lambda, where each F lambda is a mapping from the interval 0, 1 into G, is a homeomorphism of 0, 1 onto a subset of G. Let's call it G lambda. So we're not saying that it's a homeomorphism with G. We're saying that these intervals are a homeomorphism with a subset of G. We're going to give some examples to show how it works. But the intuition here is that these are going to represent your edges, right? They're edges, they're intervals. And furthermore, with the property, with the property that G is a union of its edges, right? That makes sense. You're basically trying to say your topological space is made out of what we want to call edges, just like we have in a graph. So it's made out of edges. And if you have G lambda, let's say G lambda 1 and G lambda 2. So if you have two edges, two different edges, and you intersect them, then they will intersect into something that's empty, or they might intersect, but if they intersect at just a single point at the endpoints. Or what would happen is, if they intersect, that's the other thing that can happen, they intersect at an endpoint. So it would be F lambda 1 at 0 or 1. F lambda 2, 0 or 1. If that's unclear, the example will clarify that. So some people, I would say most people, also require that G is Hausdorff. I'm not sure if I don't think we're going to actually need that, but some people will put the requirement that your topological space should be a Hausdorff space. It might feel a bit unusual because look at this: G is a union of G lambdas, and every G lambda is homeomorphic to this interval. So this interval is Hausdorff. So it seems that G should be Hausdorff because it's a union of Hausdorff subspaces. But I'm going to show you a very bizarre example where that does not have to be the case. So most people also require that G is Hausdorff, and that G is connected. And if you do not like connected, you can just say path connected. It's a path connected space like we've always been assuming up to this point. Now, let me just add this. For simplicity, we're going to assume that lambda, which is the indexing set, is finite. Later on, I'm going to show you how you can generalize it to an infinite indexing set, but things do become a little bit trickier when you do that, not surprisingly, when you have an infinite collection. Let me just say one more thing in this definition before I finally show you some examples. So this is a definition that does not end. It seems to just keep on going and going. The subsets G lambda are called the edges of the graph. And if you take each of these mappings and you evaluate them at the endpoints, so let me write it a little bit larger. And if you take each of these mappings, f lambda, and you evaluate them at the endpoints only, so not on the whole interval, but specifically on the endpoints of the interval, and you take their union, then you call these the vertices of G. Okay, so this is the definition. I know it's very long, but the piece that you really want to pay attention to, like the main part of the definition, is really this. So this is really the main part of the definition, that when you say that a space is a graph, topological graph, there's a collection of homeomorphisms mapping the unit interval into your space, and they're mapping the unit interval homeomorphically to a subset, and the requirement is that these, well, we're calling them edges, but the requirement is that these edges, together, when you take their union, they should exhaust and give you the entire space, and they intersect in a nice way, that when you intersect them, there's no overlap. So of course, I forgot to write it over here, but I'm sure it's understood, assuming that lambda 1 and lambda 2 are different. So if you have two different indices, then they intersect empty, or if they do intersect, they intersect at an endpoint. So it's the homeomorphism map evaluated at 0 or 1. It's right at that endpoint. That's the way they intersect. So now let me show you some examples to help clarify what we mean. So this is what we call a one-dimensional triangulation. One-dimensional triangulation. One-dimensional triangulation, it's a collection of these mappings that have that property. It's one-dimensional because the unit interval is one-dimensional. Later on in the semester, we'll talk about higher dimensional triangulations, and you will see that this is actually a very similar definition. So now let me show you some examples to illustrate this definition. So let's start with the circle. Example S1 is a graph. So why is it a graph? So here's why it's a graph. So here's the circle, and we can triangulate it. So what does this mean? That means we can find a homeomorphism that maps this interval to this piece. And let's call this homeomorphism F1. So it maps this interval to that piece, right? That interval is homeomorphic to that arc. Then we have another homeomorphism from this interval, the interval from 0 to 1. Let's call this F2. That's a homeomorphism. And then we have another homeomorphism mapping this interval into F3. And so if we call this, so let's call this G for graph, then notice that you have three mappings, F1, F2, F3. Each of these mappings maps the interval homeomorphically to a subset of G. And then if you take the union of these, so your edges, so this one over here, we're going to call this one G1. That's the corresponding image. This one we're going to call G2. That's the corresponding image. This one we call G3. And then it's easy to see that G is then the union of its edges. It's the union of these edges. And now look at this. How do they intersect? So this condition is satisfied. We have homeomorphisms, and G is the union of the edges. And when they intersect, if you take two different edges, they will intersect either empty or they intersect at a single point. So you can see this. Like, for instance, let's say we take G2 and we intersect it with G3. What do we get? Well, we get they meet at exactly that point right over there. That's the point that they meet. And how do you get the point? Well, the way you get the point is you can use F3. If you use F3 and you evaluate it at 1, right? You evaluate it at this endpoint, then F3, when you map that, it gets mapped to the intersection. But that's also the same thing as F2 evaluated at, in this case, it's the other endpoint. So let's say this interval is being mapped. This one goes there, that one goes, let's say this one goes there, that one goes there. So this would be, let's say, at 0. I mean, it does not matter whether it's 1 or 0. Like, the only thing that matters is when they intersect at a common endpoint. It's the endpoint of the mapping interval. So that's the way they intersect. Okay, so S1 is a graph, and it has a triangulation with 3 edges and 3 vertices. Now, here's what you need to understand, and this is a very important point, is this is warning. In topology, the triangulation is not given to you. Rather, a graph is something that has a triangulation, and it might have many different triangulations. That's just one way to do it. So you could find a triangulation with 3 vertices and 3 edges. But you can also do it differently, and you can easily imagine many other ways you can do it. You can take the same circle and you can triangulate it like this. And then you have 4 vertices and you have 4 edges. So this is like the contrast with a discrete graph. In a discrete graph, you must be given with the vertex set and the edge set. In topology, you rather start with a topological space. And if that topological space can be what we call triangulated in that way, then the triangulation gives you vertices and edges. The vertices and edges are not part of the topological space. So that just depends on how you choose to triangulate. Maybe give you some more examples. So give you some more examples. The figure 8 space. This is a graph. And here's one way you can triangulate it. You can kind of, maybe this is one edge, then you have another edge like this. And then you have a third edge right over here. The important thing is that when the edges intersect, they intersect in just a single vertex. And then you can maybe put this, and then you can have another edge going like this, and you can have another edge going like that. And then you can see that the property is satisfied. These are homeomorphisms, and if you pick any 2 edges, 2 different edges, their intersection, like these 2, they do not intersect at all. And if they do intersect, they only intersect at the common endpoint of the 2 homeomorphisms. Now, an example of something that is not an allowable triangulation would be, let's say you were to do this. That would be one mapping, and this would be the other mapping. This is no longer allowed, because then these 2 subsets, even though you are mapping the interval homeomorphically, when you intersect them, they're no longer intersecting at a common endpoint. They're now intersecting at 2 common endpoints, so that would not be allowed. Though there are some people who would allow that in their definition. I just decided to keep it as simple as possible and not allow things like that. Of course, if you have things like that, you can further subdivide them even further so that it is consistent with the definition that we gave. That would be a graph. Another example of a graph would be the interval itself. That would be a graph. You can, of course, subdivide it into 2 pieces, and that would be one edge, and then you would have another edge. But there's no need to do that. You can, of course, just map the whole interval, and then you have 1 edge and 2 vertices. The point is, the triangulation is not given to you. So when you say that something is a topological graph, then you're just saying that it is a space that has a triangulation. Now, I want to just get to this issue. This is some bizarre stuff. So we said that some people, I do not think it will matter for what we do, but some people also require that G is Hausdorff, which at first seems a little bit bizarre because G is a union of edges and every edge individually is Hausdorff. But I want to show you an example of a very bizarre example of when that will fall apart. And then some people will tell you that is not a graph. The reason why people want it to be Hausdorff is because when it is Hausdorff, certain nicer properties end up working out. But let me just give you an example. Those of you who've had topology the previous semester, we talk about this somewhat bizarre space. It's called a line with double point. So you have a line here, let's say from -1 to 1, and then where you have an origin, you have 2 zeros. One of them is 0 plus, and one of them is 0 minus. And these 2 zeros, so you kind of remove this 0, so you have a hole in your space, but you do not really have a hole in your space because you fill it in with these 2 zeros. And these 2 zeros, they're infinitely close to the line. So your topological space, it would be the line, let's say from -1 to 1, and then you're going to remove the number 0, and then you're going to attach two new symbols. One of them is 0 plus, and one of them is 0 minus. So this is what you call a line with a double point, and now you have to topologize it. So here's how you topologize it, and then you say that U is open in X if and only if for any point P in U, we can find there is, let's say, an epsilon bigger than 0, so that the interval from P minus epsilon to P plus epsilon is contained in U. That's the way we define an open set. And here it is understood that if the point that we pick is this double 0, then P minus epsilon and P plus epsilon, this will then play the role of 0. So you're just having two different symbols, but algebraically, it behaves like a regular 0. So if you have, let's say, 0 minus epsilon, that's just minus epsilon. So that's the way you topologize this thing. So you have a set, and you have a topology, so you have a topological space. And now this is a graph, okay? So X is a graph because you can triangulate it. So here's how you can triangulate it. You can, for one of the edges, this can be one of the edges where it's 0 plus, and the other edge would be 0 minus. So those are the mappings. At first, you might be a little bit worried. You might ask, is it really true? Like, is it really true that the interval from 0 to 1 is being mapped homeomorphically to this? Yes. This 0, it's not actually away from the origin. It's infinitely close to the origin. It's just that we're just drawing it that way so it's easier to see, but it's infinitely close to the origin. So this interval is being mapped homeomorphically to that. And in the exact same way, this interval from 0 to 1 is also being mapped homeomorphically to this piece. And then you will notice that if you take these two edges, this edge and this edge, if you intersect them, there is no intersection because the place where they should intersect, which should be 0, there's two different zeros, so they do not intersect. And furthermore, this is a graph, but is not Hausdorff. And the reason why it's not Hausdorff has to do with the fact that these two zeros, you cannot separate them by open sets. So let's see what would happen if we try to separate these two zeros. So you would have to, if you draw an open interval containing this 0, the moment you draw an open interval, it will spill over back over here. You will have that missing hole. It will spill over and will contain the regular real numbers. And when you draw an open interval around that one, it will contain this one. It will contain that 0. It will contain that 0, and it will then immediately spill over back on the real interval. And then you can see no matter how small you try to make them, the two open intervals that contain these two will always intersect. So you cannot separate these two zeros by open intervals. So because of that, the space is not Hausdorff. So it means that there's some people who would look at this example and they will tell you that it's not a topological graph, because some people insist that a graph should also be Hausdorff. There's certain instances where that's useful to have. The other thing I wanted to talk about is, can a graph, well, maybe we can talk about this. Can lambda be infinite? So can you allow an infinite indexing set? And the answer is yes, but we need additional conditions. So I'm going to write down what those conditions are for the sake of completeness, so you get to see what that is. But it's not something that we really are going to use. I guess it's just something that's nice to know in general. And the purpose of these conditions is to remove certain pathological types of graphs that you do not want to treat as graphs. So let's take this down and say what those conditions are. Now, if lambda is an infinite indexing set, then we require that the topology of G, so G, this is your graph, your topological graph, is coherent, or you can say maybe compatible, consistent, with the topology of each edge. So recall that G is a union of its edges. So you want the topology of the entire graph to be consistent with the topology coming from each of the edges. So what do we mean? So more precisely, we would say that U is open in G. So a topology consists of open sets. So we have to just say what the open sets are. So if something is an open set in G, then it's certainly the case that if you intersect it with G lambda, then that's going to be an open set in G lambda, because that's the way it always works. This is open in the entire space. G lambda is a subspace. So if you take an open set and you intersect it with a subspace, you get, by definition, an open subset of the subspace. So when we say it's coherent, we mean it's also true the other way around. Okay, so this direction, this is always true. So it's the other arrow that makes it what we call a coherent topology, that you can recover the topology on the entire space from the individual edges. So let me give you an example, and we've used this example already before. This is our third time using this example, but this is the example of the Hawaiian earring. So let's say G was to represent the Hawaiian earring. It would be a circle, and then you have another circle, and then you have smaller diminishing circles like that. Maybe I should call this a non-example. So the Hawaiian earring is not a graph. I know it looks like it's a graph, right? It's made out of edges. It looks like it. But here's the problem that occurs. So you could say, well, what exactly would be the problem if you tried to triangulate it? So you can triangulate it like this, right? You can you just have to use infinitely many of them, right? But you can easily see that you can build this out of edges. Absolutely. You can build it out of edges. You can absolutely do that. But what's going to happen is that when you build this out of edges, the topology that you get coming from the edges will not be coherent with the topology that you started with. So here's an example that's going to show it to you. So let U represent the following subset. So we're going to go to that point where everything comes together, and we're going to draw an open arc like this, and we're going to draw another open arc like that. We're going to draw an open arc like this. We're going to draw an even smaller open arc like that. So then U, when you intersect it with any edge, let's say G lambda, is open in the edge. Okay, so let's say one of these edges is all the way out here, right? Let's say this is G lambda. Then it will not intersect with U. It's empty. So empty, that's an open subset of G lambda. But if it's, let's say, this red one over here, when you take U, when you take this U, and you intersect it with, let's say, this edge over here, what do you get? Well, then you will get, so you will either get something that's empty, but maybe you'll get something like this or something. Right, so if you're using this one. And we can agree that this is an open interval, right? That's an open, that's going to be an open set. That's an open set. So that's an open subset. So whatever this is an open subset, is an open subset of G lambda. And G lambda would just be this entire thing, including the endpoints. Right, so that would be, and it does not matter which one you use, right? There's infinitely many edges, but when you take this figure and you intersect with each one of them, you get an open subset. So we see, so thus, this U is open in each G lambda. And when we say U is open, we're being a little bit sloppy. Really what we mean is U intersected with G lambda is open in G lambda. So each of these are open subsets of G lambda. But U is not open, not an open subset of the entire space G itself. Why not? Well, it's impossible to get a figure like this no matter how small you make your interval. I mean, you can, I'm sorry, I did not mean to say interval. I mean to say how small you make your disk. So let's say you have this. No matter how small you try to draw a disk and you intersect the picture, what you get, here's the way it's going to look like. You're going to have this, then you're going to have this, then you're going to have this. But then eventually the circles get sufficiently small enough and you start seeing those infinite loops. No matter how small you draw a little disk around that point, you will always see these arcs and then you will see loops. There's no way how you could make those loops go away. You will eventually see them no matter how small you make that disk. But in our example, we're getting this figure over here that never contains any of those loops. It's these, all of these are open, all of these are the open arcs, and we see that when you intersect it with this triangulation, you're getting something that is an open subset in each of the arcs, but it's not an open subset of the entire space. So this would be an example of something that is not a graph. So the Hawaiian earring is not considered to be a graph anymore. It's, I know it looks like a graph, but we do not permit that to be a graph under our definition. So, so this is what happens when you have an infinite indexing set. And an interesting exercise that you do not have to do this exercise. It's not like we're really going to use this because this is point set topology. But an interesting exercise is to show that if you assume that G is Hausdorff, so this is going to be one of those instances where you're going to see why it's important that the space is Hausdorff. So if you assume that G is Hausdorff, and lambda and G is triangulated with a finite indexing set, so if G is Hausdorff, so you assume that the graph is Hausdorff from the very beginning, and you assume that your graph can be triangulated using finitely many edges, so then the topology of G is coherent with the topology of each G lambda. So this is what happens when it is finite. So it's an interesting exercise. It maybe makes you appreciate a little bit more why you want to assume it's a Hausdorff space in the beginning, but it's not something that I think we're going to use in this class. So that's why it's not super important. This is point set topology, but if you're interested in that kind of stuff, you can try doing it. But now let's move on to finite triangulations. So we're going to primarily focus when we have a triangulation that consists of finitely many edges. Let us say that G has, so it is a graph, G is a topological graph with a finite triangulation. So what does that mean? I.e., there exist maps f lambda from 0, 1 into G, which are homeomorphisms of the interval from 0 to 1 onto a closed, well, let's just say it has to be a closed subset. If you assume that G is Hausdorff, then it has to be a closed subset. But let's not even go there. Onto a subset G lambda of G. So then such that G is the union of all of its edges and ... So the additional properties are satisfied. Namely that if two edges intersect, then it's either empty or they intersect in a common endpoint. And let's just assume that this this index set is finite, and lambda is finite. So this is what we call a triangulation. So suppose this triangulation consists of V vertices and E edges. Let's quickly remind what the vertices are. So the vertices, it is the union. So you're going to take each of these homeomorphisms and you're going to evaluate them at the endpoints. So that's why I'm writing set 0, 1, because you're just evaluating them at those 2 points. So they're going to give you 2 points in G, and then you're going to take the union over all of these maps. And the set that you get, you call that the set of vertices. The edges that you get is exactly what we call G lambda. And G lambda is the image of these homeomorphisms. So we're saying, suppose we have triangulated the graph in this way, and we have V vertices and E edges. And as we've said before, here's a warning. We've said this before, but this is an important point. The number of vertices and edges depends on the triangulation. If you have a different triangulation, you'll have different numbers. So the same topological space, the same graph, can be triangulated many different ways. Now we're going to define a quantity that, interestingly, never changes. We're going to see that very soon, but a quantity that never changes. So the number of vertices and edges could change depending on the triangulation. But let's define the following quantity. So here's a definition. The quantity, so if you take vertices minus edges, so this quantity is called the Euler characteristic of the triangulation. So a triangulation, by definition, it's a collection of these mappings. So it is called the Euler triangulation. I'm sorry, the Euler characteristic of a triangulation. And what is amazing is you can write this as a theorem. It's actually not that difficult to prove, but it's a surprising result. The Euler characteristic is a topological invariant, i.e., it only depends on the topology. It does not depend on how you triangulate. You can triangulate many different ways, but that quantity, when you take the number of vertices minus the number of edges, the number that you get will always be the same because it's the same graph. So for example, just to show you an example, let's say we take the circle. If we triangulate the circle like the way we did it before, the number of vertices is 3 and the number of edges is 3. So then if you do v minus e, you would get 0. Now, if you were to take the same circle and you triangulated using 4 edges, then the number of vertices would be 4 and the number of edges would be 4, and still v minus e would be 0. Now, if you take the figure 8, then the figure 8 space is topologically distinct from the circle. So therefore, we anticipate that maybe when you triangulate and you calculate the Euler characteristic, you're going to get a different number. So we can try doing that. So here would be one way to triangulate. Again, there's lots of ways to triangulate, but this would be one way you can triangulate. And if you do it like this, you count the number of vertices. So that would be 1, 2, 3, 4, 5, 6, 7. And then you count the number of edges, 1, 2, 3, 4, 5, 6, 7, 8. And then vertices minus edges would be -1. So you will have -1 as the Euler characteristic. And then according to this theorem, it then would not matter how you triangulate. The number will always come out to be the same. To give you another example, let's say you take this interval and then you triangulate it. So as you can see, it would not matter how you triangulate it, but if you triangulate it like this, the number of vertices would be 3, the number of edges would be 2, and then the Euler characteristic would be 1. So now I just want to caution you that it is possible that you might have perhaps spaces, topological spaces that are not homeomorphic, but they might have the same Euler characteristic. So you just have to be careful with that. But what we are saying is that it is a topological invariant and it does not depend on the topology. We're going to prove this. It is possible to prove this theorem using a very elementary argument, but we're going to use a very fancy argument that uses the fundamental group. I think it's going to be a very cool illustration of the techniques that we've talked about at this point. And because of this theorem, we can now make the following definition. So let's take this away. So let's remove this. And let's make this definition. Let G be a, so let's call it a finite graph. A finite graph. So what do we mean by a finite graph? We just mean G has a finite triangulation. So the number, the index number that you're using for lambda is a finite number. Because if it's an infinite number and the number of vertices and edges is infinite, then it becomes a bit unclear how you would define that quantity. There are ways to do it, but we do not want to go there. So assume that G is a finite graph. So finite graph just means it has a finite triangulation. Then we define chi of G to be the Euler characteristic of G. And it is computed by using a triangulation. So you choose a triangulation, and after you choose your triangulation, that difference is the way you find the Euler characteristic. Based on this theorem, it will not depend on how you triangulate, and so regardless of how you do it, you will always get the same number. So this is a well-defined notion. Now, some of you possibly have seen the Euler characteristic before, maybe in the previous topology class, or perhaps even in other areas of math. Maybe you read about this. So I just want to give you I just want to show you how it's connected to the Euler characteristic that you've seen before. So you probably seen this before but not for graphs, but rather surfaces. And you talk about the Euler characteristic of a surface. So a triangulation of a surface is a decomposition into triangles that fit nicely together. This is not a formal definition, and I do not want to give a formal definition, because later in the semester we will talk about triangulations of topological spaces in general, not just surfaces. If you do not know the formal definition of the surface, that's okay. I just want to present this as something you might have seen before, and then when it becomes appropriate later on in the semester, we'll give a more rigorous definition when it becomes appropriate. At this time, I just want to show the connection to Euler characteristic of surfaces. The way this works is that the idea is you have some kind of surface, let's say like a torus or something. You have a torus, and a triangulation would mean, it means exactly as the name suggests. It means you break it up into triangles in some kind of way like this. So it's similar to a graph, except it's done with 2 dimensions. So these are 2-dimensional triangles. You sort of cut it up into pieces, and then the Euler characteristic of a surface, once you triangulate your surface, it would be the number of vertices minus the number of edges plus the number of faces. So these are vertices, and the F are faces. Faces just means triangles. How many triangles are you using? So for example, the sphere, it's homeomorphic to the cube. It's homeomorphic to the cube. And when you have a cube, you can then count how many vertices you see. So the number of vertices here is equal to 8. You can count how many edges you have. So that 1, 2, 3, 4. Then there's 4 in the back, and there's 4 on the side. So that would be 12. And then the number of faces, there's 6 faces. So if you do 8 minus 12 plus 6, that will give you 2. So you end up getting the number 2. By the way, the pattern is, this is the way you memorize it. Vertices, this is 0 dimension, because it's just a point. Edges are 1-dimensional, and faces are 2-dimensional. And then the pattern is plus, minus, plus, minus, plus, minus, and so on. So it's an alternating sum. You start with the smallest dimension and you alternate it. So you could define Euler characteristic of higher dimensional topological spaces also, and that would be the way you do it. So then instead of having triangles, you will have tetrahedron and so forth. Technically they're called simplices, but as I indicated, we will get to that and we will define it when it becomes appropriate. But for now, I'm just trying to give you an idea. So the Euler characteristic of the sphere would be 2, but you can also do it a different way. You can also say the sphere is homeomorphic to a tetrahedron, and then the number of vertices would be 1, 2, 3, 4. So there's 4 of them. The number of edges is 1, 2, 3, 4, 5, 6. And the number of faces, 1, 2, 3, 4. And as before, if you do 4 minus 6 plus 4, you get 2 again. So there's actually a famous theorem in geometry that you've probably seen before, and maybe you wondered how you prove it. And the theorem says that if you have a polyhedron, maybe to be safe, we can say a convex polyhedron. So if you have a convex polyhedron and you count how many vertices, edges, and faces you have, if you add up these numbers, it will always give you 2. So that's something that Euler realized back in the 1700s. So Euler accidentally discovered a topological invariant, because all of these convex polyhedron, they're all homeomorphic to the sphere. And the key idea here is the Euler characteristic is a topological invariant. And that's going to be something we will do later in the course. We're going to define it rigorously, and then we're going to prove it with the machinery that we develop. But the reason why I bring this up is because it connects very nicely to what we have with a graph. A graph, it's a 1-dimensional object, So when you triangulate, you only have vertices and edges, and then you do the alternating sum. You start with vertices, which are zero-dimensional objects, and then you would subtract away the edges, which are the one-dimensional objects in the triangulation. And that difference is a topological invariant. Now, what I want to move on to next is, in order to prove that it is a topological invariant, and furthermore, we're not just going to prove that it's a topological invariant, we're actually going to do more than that. We're going to calculate the fundamental group of any finite graph. So here's the way we do it. So we need a proposition plus definition at the same time. So you're going to see what I mean. The proposition will assert that something happens, and whatever happens, the property that we seek, we're going to put it into a definition. So here's the way this goes. So let G be a finite graph with triangulation. So it has a triangulation, F lambda, lambda in capital lambda, where the triangulating set is finite. Then we can find, now whenever we talk about graphs, we assume it's a connected space, a path-connected topological space, because that's what we always assume our topological spaces are. As we remark, you can also assume that G is Hausdorff, because when people talk about graphs, they assume it's a Hausdorff space. Though, as I said, I do not think we actually need it, but there's not really any harm in assuming or not assuming it for what we do. Then we can find, so the proposition says, then we can find a sub-triangulation. So that would just mean F lambda, lambda in, let's say, lambda 0, where lambda 0 is a subset of lambda. So that's what we mean by a sub-triangulation. So you just fewer of them, such that if you take the edges, so if you take the union of all of the edges in the subtriangulation, right? So we know that if you take the union of the edges over all of lambda, you get the full graph that you started with. So this is going to give you a subgraph, such that this is, so it's going to be a graph such that this contains all the vertices. So you have to be a little bit careful. There's no such thing as the vertices of G. It's the vertices with respect to a triangulation. So it's going to contain all of the vertices with respect to the triangulation. And let's call this object T. Let's call it T. And T is a tree. What do we mean by a tree? So in a discrete math class, the way you define a tree might be a little bit different from the way we're about to do it. But because this is topology, I think this is the nicest way of defining a tree. And T is a tree. It means that, i.e., T is contractible. It's a contractible space. So contractible space means the entire space can be shrunk down to a single point. So that's the proposition and definition. The proposition tells you that you can always find a subtriangulation. The definition is, what's the name of this collection? So we call this collection, we call this subtriangulation so you can call it a spanning tree. Spanning tree. So you call it a spanning tree because it contains all of the vertices of your graph. Technically, all of the vertices with respect to the triangulation. So you call it a spanning tree, or some people call it a maximal tree. And let me just make a comment. Note, this result is also true for graphs in general. We are assuming that we have a finite triangulation. But even if the triangulation is not finite, this is still true. It just takes more effort to prove. And the proof is very boring. So I'll just give you a very quick outline of how the proof goes. The proof is actually in the name of this tree. It's called a maximal tree. So maximal means as large as you can go. So the idea here is that you're going to look at all of the trees that sit inside your graph. Again, technically inside your triangulation, but I'll keep on abusing language and calling it the graph. So you're going to look at all of the trees that sit inside the graph. So a tree is something that is contractible. So for example, any single edge, any one of these g lambdas individually is contractible because they're homeomorphic to the interval from 0 to 1. And then you're going to look at the largest possible tree that you can find. Let me take it back. Not necessarily the largest possible tree, but the maximal tree. You just keep on building that tree until you cannot add any edge to that tree. You just keep on building it, and as big as you can go, that's called the maximal tree. It cannot be made any bigger. So then you're going to have something, so you're going to end up having some kind of tree. So you're just as big as you can possibly go. And then after you're done, this is a maximal tree, you're going to claim that this tree is a spanning tree. It contains every vertex. And then the idea is, if it did not contain a vertex, if there was a missing vertex, then, now I'm going to simplify this a little bit. It's actually a little bit more complicated than this, but assume for simplicity that there's a vertex that's not part of the tree. Then that would mean that you can, well, for simplicity, let's say you could draw an edge. You can draw in an edge that connects it to one of the vertices that you already have. And then look at this. If this tree was not a spanning tree, and if it missed a vertex, then by adding in that edge, you've just contradicted the fact that this is a maximal tree. You could have made it bigger. Now, the reason why this is a simplistic argument is because this vertex does not necessarily connect to any of the edges. It could be a little bit more complicated than that. Maybe it has to take a detour to somewhere else, and then that other vertex then connects to that one. So there's a bit more work that is required, but that's roughly the idea. It's not a very exciting proof, but that's the way you do it. There's also a question in computing. So there's a problem. There's a, like a question in computer science. How to find this tree. Because if you're thinking like a mathematician, you just say it exists. You do not have to find it. You just say that the maximal tree, any maximal tree that you find, will have the property that you seek. But like a much more practical question can be, how do you actually find it? Let's say you have a graph that has millions of vertices and billions of edges. How do you end up finding it? You cannot just randomly go through all of them and hope that you find something. So there has to be some kind of algorithm that will find for you this tree. But we're just going to accept this result, and we will use it. And as we remarked, this is also true when you have an infinite graph. But in order to prove it, finding the maximal tree will use a technique that you've possibly have seen before. It's a more advanced technique called Zorn's lemma. So that's the reason why we're not going there, and also we do not need it. That would just take us way too far off topic. Now, I like to mention a theorem about the fundamental group that we've not used before, but it's going to be very useful in calculating the fundamental group of a graph. So here is a theorem. So suppose X and Y are topological spaces, are homotopy equivalent spaces. Let me quickly remind you what that means. That means there's a mapping from X to Y, and there's a mapping from Y to X, so that if you do this composition, it's not necessarily the identity on Y, but it's homotopic to the identity on Y. And when you do it like this, you get something that's homotopic to the identity on X. That's what it means to be homotopy equivalent. What it means is that X and Y could be different topological spaces. They do not have to be homeomorphic, but you are saying that it is possible to continuously change x into y. That's what you're saying. So if x and y are homotopy equivalent spaces, then the fundamental group of x, and you notice I'm not even referencing the base point, because regardless of what base point you pick, these fundamental groups are going to be isomorphic to each other. We are always assuming our spaces are path connected anyway, so it doesn't matter where you choose the base point. So this fundamental group would be isomorphic to that fundamental group. So this is a result that we have never used before when we talked about the fundamental group, for the simple reason is that we never really needed it. And also, when we start talking about homology very, very soon, we're going to have a very similar result for homology. So we're going to see that if you have two spaces that are homotopy equivalent, then the homology groups will be isomorphic. So because of this, it will feel a bit too much of a wasted class time to prove this very carefully, because we're going to see this result again for homology. So I'm just going to leave it like this, and we'll talk about why this works in the homology setting when it comes up again in the semester. But I just want to write down this theorem. It's a very useful theorem for computing the fundamental group, and we'll see how it's helpful in finding the fundamental group of a graph. Okay, so here's the problem. So the problem is this. Problem. So given a graph, let's say a finite graph G, how to compute the fundamental group of the graph. And this is the idea, is you first find a maximal tree that's contained in G. Then you collapse T down to a single point. Why can you do it? Well, because it's a tree, so it can be collapsed down to a single point. It's a contractible space. That's the reason why you can do that. And then you will be left with a bouquet of circles. So that's the process. You first find a maximal tree, then you collapse the tree down to a single point, and then afterwards you're going to compute the fundamental group of the bouquet of circles. So to illustrate this, so let me illustrate this. So this is a famous graph. You've probably seen this before. This is the three utilities graph. So you have three blue vertices. That's what the 3 represents. And then you have 3 red vertices. And then between any blue vertex and any red vertex, you have an edge. So you just draw them in here like this. And then you have one going like that, one going like this, have one going like that. Then maybe for this one, I should give a little bit more room. You have one going like that. You have one going like this. Okay. And now you see, it appears it's not possible to connect these two without crossing over. In a topological graph, this is different from a discrete graph. You're not allowed to cross over. And we actually talk about this in the first semester course in topology. We discussed this interesting problem called planar graphs, about whether or not you can embed the graph in the plane, and more generally, whether or not the graph can be embedded on a more general type of surface. But I mean, it does not have to be in the plane, so you can just easily imagine that this edge just goes underneath the other edge. That's fine. All you're saying is it's not possible to embed this graph as a subset of the plane. So it's some topological space, but it just does not embed into the plane. So that's all you're saying. So this is your topological space. Think of it as 6 points sitting inside 3-dimensional space, and you have some kind of topological space that is formed, and you want to calculate the fundamental group. And the way you do this is you're going to find a maximal tree. So here's how you can find the maximal tree. You can you can connect these two. Then you can connect these two. You can connect these, okay? Now I cannot go back like this. Actually, so let me do it again. I think this is the easiest way to do it. So I'm going to go from the blue one, I'm going to go to the red one. And then from the red one, I need different colors. So let's say from the red one, I go to the blue one. Then from the blue one, I go to the red one. From the red one, I go to a blue one. From the blue one, I go back to the red one. And then from this red one, I go to a blue one. I go like this. And then from that blue one, I go back to, I think that's it, right? That's it. You can see that all of the vertices, yeah, so this vertex, this one, this one, this one, this one, and that one have been used up. So this is your maximal tree. Now this maximal tree is homotopy equivalent. So now take the red stuff, because it's a tree, it collapses down to a single point. Now when you collapse everything down to a single point by using a homotopy, all of these vertices, all of these 6 vertices that you see, it will become a single vertex, right? They all of these 6 vertices collapse down to a single vertex. And how many edges? The red stuff will become a single vertex. So maybe we should just make this one big red point. That's what we have. And then the remaining edges get left over. But each of these remaining edges, their endpoints, they come together and they meet at the circle. So this one turns into a circle, that one turns into a circle. So you have to count how many remaining edges you have. 1, 2, 3, 4. So you have 4 remaining edges. So that means you will be left with 4 circles. And that's the whole point, that this graph is homotopy equivalent to a bouquet of 4 circles. So it's a bouquet of 4 circles. So thus, the fundamental group of this graph would be isomorphic to the fundamental group of a bouquet of 4 circles. So here we're using this theorem that as long as 2 spaces are homotopy equivalent, they have isomorphic fundamental groups. So the fundamental group of this space would then be isomorphic to a free group of rank 4. So this fundamental group of this is isomorphic to the fundamental group of that. And we talked about the fundamental group of a bouquet of circles. So this is therefore isomorphic to a free group of rank 4. And that's the way you find the fundamental group. And now you can turn this into a nice theorem. So here's a nice theorem. So suppose G is a finite graph. Then the fundamental group of G is a free group of rank, and the rank is 1 minus the Euler characteristic of G. So in particular, chi of G does not depend on triangulation. So you are triangulating the graph to find the Euler characteristic, but in the end it would not matter, because this quantity is expressible in terms of the fundamental group. That has nothing to do with the triangulation. And proof, well, here's something very nice. Proof. You can prove this. It's really not that difficult. The previous example that we did really contains the main idea. You just have to figure out a way how to make that a little bit more general, and then you have a proof of this result. So, for example, So for example, the interval, its Euler characteristic is equal to 1. So the fundamental group of this edge of the interval would be a free group of rank 1 minus 1, 0, which our convention is that a free group of rank 0 is just a trivial group, which makes sense because the fundamental group of the interval is trivial. If you have a circle, then the Euler characteristic is 0. And so the fundamental group of the circle would be a free group of rank 1 minus 0. So a free group of rank 1, which is the integer, so it's the group of integers. If you have a figure 8 space, then we saw that the Euler characteristic is negative 1. And then the fundamental group of the figure 8 space, that's a free group of rank 2, which makes sense. It's 1 minus negative 1, so that's 2. So as you can see, this does work out for these simple examples, but you can prove this more generally. And this is a very, very nice way to show why the Euler characteristic does not depend on the triangulation. And for those of you who are interested, when we talk about the Euler characteristic of surfaces and more generally higher dimensional objects, we will also be able to prove in the very same way that the Euler characteristic is a topological invariant, not by using the fundamental group, but by using different groups. So you can see we're expressing it in terms of the fundamental group, which is a topological invariant, but we'll be able to express it using homology groups. It'll be a very similar kind of technique of showing why it is a topological invariant. So now let's talk about covering spaces. Now here's a very nice result. Let's write this as a theorem. If G is a graph and pi, let's say from G hat to G, is a covering map, then G hat is also a graph. So that's fairly interesting. It says that the covering spaces of graphs are graphs again. And we're going to prove it in the special case. So this is going to be special case proof. We're going to assume G is finite graph, and pi from G hat to G is finite sheeted. It's a finite sheeted covering. If you want to prove this more generally, you can do it, but it's going to be a little bit more trickier because you have to use the more general definition of what it means to be a graph with an arbitrary indexing set. If you want to see a reference for this, you can look at Muncre's. The name of the book is called Topology. I'm sure you all know this book. I believe this is chapter maybe 15. This is the last chapter in the book. So he actually gets into a lot of detail about graphs, and he treats the case of when you have infinite graphs a lot more carefully. But we're just going to keep things simpler. I'm going to assume that we have a graph with a finite triangulation, and the covering space is a finite sheeted covering. So we can assume without loss of generality that G has a triangulation F lambda so that each F lambda, so the image of each of these, which we're calling G subscript lambda, right? So these are the edges, so that each edge is evenly covered. The reason why we're allowed to assume that is basically it's a trick that we've used before. But the simple idea is this is our graph, and this is the interval from 0 to 1, and we have a homeomorphism F lambda onto a edge G subscript lambda of the graph. And we're assuming that this is evenly covered. So that means you can find like an open set containing this so that the open set is an evenly covered open set. If it's not, all what you would do is it's a trick we've done before. You cut up this into smaller pieces, and then you have a partition of all of these edges. And if you make this sufficiently small enough, then you can guarantee that each of these edges will be evenly covered. So the idea makes sense, but writing out the formal details of that would be very tedious. So we're just going to begin the proof by automatically assuming that we have triangulated G in such a way. You need to understand that G is a topological space. It does not have a triangulation. So whenever you're talking about a graph, you're just assuming that it is a space that has a triangulation. So you get to choose the triangulation. Okay, so we have a triangulation. And here's what we have next. Okay, so then, okay, so say f lambda, so it's a map from 0, 1 into GL. That's your homeomorphism. And GL sits inside U, where U is evenly covered. Okay, so thus, when you pull back U using the covering map, you will have a union of path components. Let's call them V, J, J and J. So J is finite, because this is a finite sheeted covering, finite. Okay, so we have this. And each Vj is mapped homeomorphically to U using the map pi. So maybe you can say pi restricted to Vj. So these are homeomorphisms. So now look at this. We're mapping this interval from 0 to 1 homeomorphically to G lambda by using f lambda. And then this is contained in U. And then you can map U homeomorphically to Vj by using pi, the restricted map. So it has an inverse because this is a homeomorphism. So you have this homeomorphism. So if you compose them, so we get that if you do f lambda composed with pi restricted to Vj inverse, that this will be a mapping from 0 to 1 into the covering space. So these are open subsets in the covering space. So this map is a homeomorphism of the interval onto a subset of G hat. Okay, so this collection, and then you have to check. So this collection. So now you have a collection pi Vj inverse f lambda is a triangulation for G hat. So what does it mean to be a triangulation? It means that it's a collection of mappings from the interval into your space, and they have to fit together in a nice way. So first of all, the images, so the edges that you get, maybe you can even add over here, you can add that lambda ranges over this indexing set, and j ranges over the other indexing set. But this is a finite collection because you're assuming the j is the indexing set for the number of sheets. So that would be a triangulation for the covering space. You just have to check that they fit together in a nice way. And I mean, I do not want to spend more time on this, otherwise the lecture gets way too long. But I mean, the basic idea is, if this is G, I know that's not how G looks like. It's a graph, but that's not the point. So if this is G, and this is an edge, right? This is an edge. This is what we're calling G lambda. So how you're doing it, you're saying that you're assuming that the edge sits inside an evenly covered neighborhood, and when you lift it, you get this stack of pancakes, like this. And then you're getting the lifted edge in every pancake. That's what this composition is. You're getting the lifted edge in every single pancake. And now notice that these edges, they do not overlap. So if you start with the same edge, they do not overlap. Now, it could happen that, well, yeah, so these do not overlap. But it could happen that you have an edge over here, and then you have an edge over there, and they do overlap. Right? Two edges, they could overlap. So if they overlap, if you were to lift this edge, and you were to lift this edge, it could happen, right? So you lift one of them, you get this one, and when you lift this one, they have to intersect at the common endpoint. And the reason for this is because if they intersect in the cover, then their projection will intersect in the base space. So they have to intersect the right way. So they cannot, I mean, basically what I'm saying, you cannot have a situation when one edge goes like this and another edge goes like that. Because then if you were to project them, they would intersect in the wrong way in the base. So that's like the last thing you have to check. You have to actually show that that gives you a triangulation for the covering space by verifying all of the required properties. But I think that's clear enough. I mean, that's kind of like the main idea of this. And furthermore, let me also add this to the theorem. And furthermore, the covering space is a finite graph because this is a finite triangulation. Right? This is finite, that is finite. So this is a finite triangulation for the cover and the Euler characteristic of the cover would be equal to the Euler characteristic of the base, and then it gets multiplied by the sheet number. So why does it get multiplied by the sheet number? Well, because if you count how many edges you have, notice you have the same number of edges that you have before, and for every single edge, you have J, capital J, extra edges in the cover, right? So that's the sheet number. So the number of edges gets multiplied by the number of sheets. And the number of vertices gets also multiplied by the number of sheets, because how are you getting the vertices? Well, those are the fibers, right? You get the fiber over the point, that will give you the vertices in the covering space. And so everything gets multiplied by the sheet number. So the Euler characteristic will therefore grow by that multiple. Okay, so that's a nice result. That now, again, this is true even if the graph is not assumed to be a finite graph. So the go-to example is if this is the circle and G hat is the universal covering, the universal covering is that infinite tree. So it's a tree, it does have a triangulation, but you'll have an infinite number of edges required to put them together to get that tree. So it could happen that the covering is infinite sheeted, and it would be a graph with an infinite type of triangulation. But that's something a little bit more general, and we're not going to go there. But if you're interested, you can look it up in, let's say, the Moncrief's book, where he talks about that a lot more carefully. Now we're going to conclude with a very amazing theorem in group theory, and we're going to prove it using, surprisingly, topology. So it's a very interesting connection. So let's write down what this theorem is. This is a very famous theorem in group theory. It's called the Nielsen-Schreier theorem. So here's what it says. It says that if, well, here's like the very quick version of it. The subgroup of every free group is free. And I know what you're thinking. You're all thinking to yourself, how is this not obvious? If the entire group is free, why would it not mean that the subgroup is free? You have a smaller collection of objects. And I think maybe what the confusion here is that psychologically, the way you're interpreting this is that you're saying, because the group is free, it's sort of, you're basically thinking to yourself that everywhere you look, you see freeness, whatever that means. And so if you pick a subgroup of that, because it's already free everywhere, it's going to be free on that subset. But that's just misunderstanding what the theorem is saying. To appreciate this theorem a little bit more, there's a very nice example of this from Wikipedia. So if you go to the Wikipedia page for this theorem, they present a very nice example. So this is the example that they give. So G, this is going to be the free group generated by two symbols, by A and B. And H, this is going to be the subgroup of G, consisting of words of even length. So a word is just some combination of A and B. Because it is a free group, it means that every element in G is written uniquely as a product of A's and B's. You can allow inverses, of course, but it would be uniquely expressible using the symbols A's and B's. So for instance, for example, you would say that AABB is an element of H. You would say that AB, A inverse, let's say B, is an element of H. This is a word of even length. You have four of them, okay? But AAA, that would not be an element of H because you're using three of them, okay? So these are words of even length. You can have, let's say, AAAA, that's an element of H, and so on. And the reason why it's a subgroup is very simple, because the identity element, it's a word of even length. You can write, let's say, AA inverse. Well, you can also say it's a word of length 0. I mean, you could just say it's a word of length 0. But the important point here is, if you have a word of even length and you have another word of even length, if you multiply the words together, you get a word that is the sum of the lengths. So you're just adding two even integers together, so you get something that's even. So H is a subgroup. And H is generated by the following words. So you would say that if you have a word and it has even length, you just have to look at all of the possible ways you can get two even ones. So AB, AAAB, you can have BA, and then you can also throw in, maybe you can also throw in some inverses. So you can have maybe A inverse B, right? You can have, now you're not going to write AB inverse Well, yeah, let's write AB inverse. And I guess the other one we did not use is BB. So if you have a word of even length, it can be decomposed in this way. So you either have two A's together, two B's together, you have an A and the B, B and the A, and then you also can have inverses. The other ones will, like, the reason why we're not writing A inverse, because that would just be the inverse of that. And there's no need to write B inverse A, because that's already the inverse of that word. But you have these six, so you have six generators. Now, here's the whole point. So you would say that H is generated, so it has six generators. But notice something quite interesting happens, that these generators, these six generators, have relations between them. So, like, for example, let's look at this one over here. Here's how we can write it. If we take AA and we take the inverse of it, and then we multiply it by AB, we multiply it by this one, then what are we left with? We're then left with A inverse B. So you can see that this one is sort of redundant. There's a relationship. You can express this one using the first two. So this one is redundant, and actually this one is redundant also. So then you have, but then you can ask, is there any relationships between these four? So I think you can maybe eliminate, yeah, I think this one can be eliminated. BA can be eliminated. You can maybe do this. You can take BB, right? You take this one, and you can multiply it by the inverse of this. And then you have BB, B inverse, A inverse. So that's B, A inverse. But that's not giving you, it's not giving you this one. And then you can maybe multiply it by, and then if you multiply this by AA again, then you end up getting BA. So there you go. So it seems that BA is also redundant. So you can remove it from the list. So it appears we can get rid of three of them and be left with the other three. And maybe there's no generators between them. And in general, the situation is going to be a lot more complicated. This example is somewhat simple, but in general, the situation is going to be a lot more complicated. So in general, let's say G is a group that's generated by the symbols from A1 to AN, and this is a free group. And when you have a subgroup, the subgroup would be generated, I mean, assuming it's even finitely generated. It could be more complicated that it's not even finitely generated, but assuming it's finitely generated, you'll have some collection of generators for H. Let's say WM, and each WI is a word. It's a word involving these symbols. And in general, when you write down these words, there are some relationships between them. And what the theorem is saying is that even though that might happen, you can replace that collection of words by possibly a smaller collection of words, let's say W1 prime, W2 prime, W, maybe some smaller number, let's call it L, so that these generators are free. So that situation might happen. And when you formulate it in this way, it is by no means obvious why that happens. Okay, so that's the Nielsen-Schreier theorem. So the Nielsen-Schreier theorem says that every subgroup of a free group is free. So it sounds like it's obvious, but when you carefully think about what it's saying, then you quickly realize it is by no means obvious why you can replace those generators by a new set of generators that have no relationships between them. And you can even discuss the question of trying to come up with an algorithm that does that for you. And that is an area of group theory called combinatorial group theory, where that's the prime focus, trying to come up with various algorithms where you can, if you're given, like, let's say, a very concrete type of problem with very specific generators and words, to try to figure out what the new set of generators are, which are free. But we're just going to prove it using topology. So this is going to be an amazing proof. So here's what we will prove. So we will prove a variant of this theorem. So here's what we're going to prove. So we're going to say that let G be a free group of rank, let's say R, and H is a subgroup of G of index, let's say index D. So index just means how many cosets you have. I do want to warn you, it is possible that the number of cosets could be an infinite collection, and then this would be an infinite index. That is possible. The Nielsen-Schreier theorem is still going to be true, but I want to deal in like the finite case. And H is a subgroup of index D. Then H is also a free group and of rank. Its rank is going to be equal to, so I think it's 1 minus D plus RD. It's either 1 minus R plus RD, or it's 1 minus D plus RD. We're going to figure it out when we prove the theorem. So as we prove the theorem, we'll figure it out. So I do not actually know what the formula is. I just know how to prove it, and then I can figure it out. But let's go back to the example again. So G, this was free group with generators A and B. And H, this was the subgroup of all even length words. And the index of H in G is equal to 2, because if something is of even length, it's already in H, so it's in the coset H. And if something is of odd length, so just make up a word of odd length. Let's say A, B, B, A, B inverse A. How many is that? That's 6. So let's do it like this, odd length. Then this is an H. So that would be an H. So then it's a single element that's not in H times something that is in H. So the index is 2. Or maybe to put it this way, if you find that confusing, if you have 2 odd words, if you have an odd word, so if you have one odd word, so if you have an odd word, so let's say A, and then you have another odd word, then they're congruent mod H. So why is it? Well, because you can just, if you just do this, then that's an element in H. Or maybe if you do not like it, you're basically saying you can express this as this times something in H. That's what it means to be congruent. And then you have to use 3 B's, but with inverses, and then 5 A's. and in total that's 8 of them. So any 2 odd words are congruent mod H. So that means that if you have a word, it is either already in H, and if you have 2 words that are not in H, then they're congruent mod H. So mod H, you only have 2 cosets. So that's why the index is 2. So H is free. It's a free group of rank. And so what the rank would be 1 minus plus R times D. So D is the index, R. So the index is 2, and the number of generators is 2. Oh, I guess it does not really tell us 2 times 2, because then I do not know whether this is supposed to be R or D. They're going to be the same in this case. But let's just calculate what this is. So this is 1 minus 2 plus 4. So that's 3. So it's free of rank 3. And if you looked at the example that we did, it seemed that the generators were AA, BB, and AB. That's what it looked like. It looked like that every word of even length can be expressed by using a product of those 3. So therefore, it seems that the rank is 3. You might find it a bit strange that the rank of a subgroup is larger than the rank of the group from where it is coming from, but that should not really be surprising, because the words that make up H, they're coming from the original generators. So you're using more of them. You might have to use more of the original generators, so that's why the rank might actually increase. So we're going to prove, so this is the version that we're going to prove. If you want to prove the more general version, it's actually going to be almost the same proof, but it will require knowledge of infinite trees. I'm sorry, not infinite trees, infinite graphs. Okay, so let's give a proof of this theorem. So it's going to be an amazing proof, so it's an amazing connection to group theory. So proof, let G be a group, be a free group of rank, we said rank R. So then G is isomorphic to the fundamental group of X, where X, it's a bouquet of R circles. This is a bouquet of R circles. So recall the result that the fundamental group of this bouquet is equal to how many circles. It's a free group whose rank is equal to how many circles you have. Now, if H is a subgroup of the fundamental group, so it's a subgroup of G, but G is isomorphic. So let's just assume that H is a subgroup of the fundamental group. Then H corresponds to a covering of X. That was the correspondence theorem that we talked about, that the subgroups of the fundamental group, they correspond to a covering. So there's a covering of X. So if H has index D in the fundamental group, then H, then the corresponding covering, let's call it X hat, is a D-sheeted covering of X, right? So if you have a subgroup of the fundamental group, then you can find the covering, so that the fundamental group of the covering is, well, yes. Anytime you have a anytime you have a subgroup, maybe I should say it like this: a covering space, its fundamental group, is a subgroup of the fundamental group of the base. And furthermore, if you have a subgroup of the fundamental group of the base, you can find the covering that will correspond to that group. So that's the correspondence, the Galois correspondence that we've talked about. So thus, the Euler characteristic, well, maybe we can even say this, but x and x hat are graphs. So clearly x is a graph because it's a bouquet of circles. X hat is a graph because a covering of a graph is a graph. So it's a graph. And furthermore, the Euler characteristic of this graph, of the covering graph, it's equal to d multiplied by the Euler characteristic of the base graph. And the Euler characteristic of the base graph, it's the Euler characteristic of a bouquet of circles. So here you have to do a little bit of a computation to think what that is, but a bouquet of circles, its Euler characteristic is equal to 1 minus r, where r is the number of circles that you have. Okay, so that would be the Euler characteristic of this one. Okay, so thus, the H is equal to the fundamental group of the covering space, right? Because that's the correspondence theorem, that the subgroup, that's the one that corresponds to the fundamental group of the covering. But how do you find the fundamental group of the covering? So this is a free group of rank 1 minus the Euler characteristic of this covering, right? So this is a graph. How do you find the fundamental group of a graph? It's 1 minus the Euler characteristic of the graph. But what is that? It's d. So this is equal to, this is free group of rank 1 minus Euler characteristic of this. This is d times r minus 1. So in the end, you get 1 minus d plus rd. And that is the theorem. So this is the amazing theorem, that a subgroup of a free group is free, and that is the rank that it's equal to, where d is the index of the group. The situation is a little bit more complicated if the subgroup, well, I guess I took it down, but it is possible that the subgroup is of infinite index, and it's still true that that H, even if it has infinite index, is a free subgroup, but it might have an infinite number of generators, and it's almost the same proof, but then you have to talk about infinite graphs, which we did not do. But we're going to finish with this, and I think this is an amazing, you can call it application in quotation marks. It's not an application outside of math, but it's an application to a different area of math, of how you can solve this problem, this very famous theorem in group theory, by looking at it topologically. So I think this is a very amazing theorem and a very amazing proof.